now I'm going to talk a bit about the absorption of light. This is, again, something that's not covered in the textbook, and I'm presenting it because I think it's really relevant for you, and again, could be something that could go into an essay topic. So every material absorbs light in a different way. So this is an example of water. I chose water because water is similar, like your body is mostly made of water. There's a lot of other things in there that factor in heavily. But if we are looking just at water, if you look at the absorption, you can see this is a weird looking thing. So this is an absorption 1/meters. So what that means is if you have an absorption of 1, so absorption coefficient of 1 is right here, 10 to the 0 power. So at this level right here, the absorption is 1 inverse meter. And what that means is if I shine light on something, on water, with this wavelength, whatever that wavelength is right there, then by the time that light goes 1 meter into the water, the intensity of the light will have dropped by a factor of E. That's what, 2.7 or something like that. So it's dropping roughly in half, a little more than that. So every meter that you go into the water, the light at this wavelength reduces by a factor of 2. So it just, it goes down sort of exponentially as you enter the material. That's what the absorption means. So up here, if you look like a fairly small change, so this is a factor of 2 right here. If I go from 1 meter, move a factor of 2, now all of a sudden the absorption in inverse meter is now 10 to the 2. That means by the time you go in 1 meter, it will have gone down by a factor of 2 that many times. So in other words, in 10 to the minus 2 meters, so 1 centimeter, the light would have dropped by a factor of 2. So here, the light drops by a factor of 2 after a meter. Here, it drops by a factor of 2 after 1 centimeter. Here's 1 millimeter. Here is 1 micrometer, so 10 to the minus 6 meters. So the light at this particular wavelength goes a tiny, tiny fraction of a millimeter into the water. So you can see it changes rapidly in some areas and then more slowly in other areas. Now that's important, for example, if you want to microwave food. If you want to microwave food, you want the microwaves not to all get absorbed in the very edge of the material, otherwise the outside of it will get extremely hot while the inside stays cold. You also don't want it to be, if I have a piece of food this big and my absorption length is 50 meters, that means only a very small amount of the light will get absorbed by it. So in a microwave, the absorption length of water in a microwave is about that long, about the size of a piece of food, to give you the best efficiency there. So as we look at this, you can see this is just for water. So you can see that you can specifically choose wavelengths to go a certain distance into a material. So that's an important thing for imaging.